Hi, my name is Nathaniel, and I'm a final year EEE student participating in the FYP Challenge 2024. When we talk about enhancing the contrast of an image, there are many ways of doing it. In my project, I will be sharing with us one such technique called CLAHE implemented on an FPGA. CLAHE stands for Contrast Limiting Adaptive Histogram Equalization. This algorithm first splits the image into equal segments called tiles and generates a histogram and a cumulative distribution function, or CDF, for each tile. The CDF is used in the transformation function and interpolation equations to generate the output pixels of the enhanced image. An FPGA stands for Field Programmable Gate Array, which is a programmable logic device used for fast, real-time, and computationally intensive tasks. This project uses a Zynq system-on-chip, or SoC, which integrates both the FPGA fabric and an ARM processor onto a single chip. Using the FPGA as our hardware, we aim to do three things. Firstly, to improve the contrast of 14-bit IR images. Secondly, to hit a data throughput of 30 frames per second for an image size of 640 by 480. And lastly, to utilize an acceptable amount of resources in the FPGA to run the algorithm. And this is how I achieve my objectives. The CLAHE algorithm is coded using Vivado High-Level Synthesis, or HLS, a tool used to implement algorithms coded in C onto the FPGA. The algorithm is split into three HLS blocks, one for CDF calculation, another for the computation of enhanced pixels, and the last for downconverting the bits to an 8-bit output. The floating point division operations in the pixel data calculations are executed in an external floating point IP core. This is done as the division operation executes at a faster speed of 4 clock cycles compared to the division done in the HLS core, that being 7 clock cycles. This was a significant design implementation as it increased the throughput of the algorithm by 2 times. After the design has been synthesized and implemented, the bitstream is exported to Xilinx SDK, an IDE used to code onto the ARM processor. Once Xilinx SDK opens up, we can now set up Teraterm. Teraterm logs and saves the outputs in a text file to be read later on. The code initializes and starts the operations of the three HLS blocks and outputs all the values of the enhanced pixels on Teraterm. In this example, we will save the text file as 16tau_080424. At this point, we have to make sure that the FPGA is switched on and connected to the laptop. The following are the steps to run the code on the FPGA. The output on Teraterm will be the CLAHE enhanced pixel data. After Teraterm has successfully logged all the pixel data, this text file will be read on Jupyter Notebook to visualize the pixel data. And finally, we can obtain the CLAHE enhanced image. After many months of hard work and testing, I am proud to share that the project objectives have finally been achieved. The input image from this has turned into this, after running it through CLAHE. The throughput was recorded and displayed on Teraterm, which gave us an average of 37 FPS, more than the objective FPS. This was mainly due to the external floating point IP core taking less time for division operations compared to the HLS core. The resource utilization objectives was also achieved with less than 50% utilization for most resources due to the streamlining of the code. And just for consistency, here are more IR images enhanced by the same CLAHE algorithm. As you can see, there are significant improvements to the local contrast of the images. With these objectives achieved, the groundwork has been laid for real-time application of CLAHE on the FPGA, making it very suitable for military surveillance and night vision applications. Thank you so much for watching this video. If you found this project interesting, I would really appreciate it if you could show your support by voting for me for the FYP Challenge 2024. It would really help me out a lot. Thank you so much once again, and I'll see you all soon.